speak, so it's a great honor to be here. I never imagined I would be speaking at the same session with Edward Witten. Yeah, so this talk is based on discussions which started at annual Simons meeting a couple of years ago, where I was sitting next to Alexei Borodin, who is a mathematician at MIT. So, and it's based on, basically, it's an attempt to translate some of recent mathematical results in the field of integral probability to quantum physics. So this thing stopped working again. Okay. So this is the outline of my talk. So the talk will be roughly about various types of dimer models, so domino coverings, which have been studied for a long time. So I'll start with an intro into these models. And then I'll talk about quantum version of these models based on so-called Rock-Shark-Evelson construction. And mention some very curious results, which started with the work by Peter Shor, Prop, and Jakush, which basically suggests that the phases in some models depend on the boundary conditions, which kind of goes contrary to the thermodynamic limit idea. So we'll talk about that. And then I'll try to transplant these interesting results to quantum spin models and talk perhaps about some mathematical techniques which are really, really interesting. So domino tilings is simply a combinatorial object that is a covering of a discrete domain. For example, in this case, it's just a square with 2 by 2 rectangles or dominoes. So arranged so that there are no overlaps and no gaps. So this is, again, a possible tiling of an 8 by 8 square. And this is a possible tiling of another shape called Aztec diamond. And in principle, you can imagine all kinds of shapes. And actually, if you put additional constraints on these tilings, so these problems become very complicated very quickly to the point of becoming NP complete, et cetera, whether it even exists a domino tiling. So, and very closely related to domino tilings are dimer coverings. So this is kind of a playful title by paper by Richard Kenyan and Andrei Okunkov, which discusses dimer coverings, which is a graph composed of vertices and edges. And so dimer covering covers all vertices exactly once. So in some sense, it's exactly the same thing as a domino, except the study, mathematical studies usually focus on these dimer coverings as classical statistical mechanical models where they assign a certain weight to each edge and therefore Gibbs measure or Boltzmann weights and study these objects from StatMech perspective. But unlike the physicists who usually work in thermodynamic limits, so mathematicians oftentimes study all kinds of shapes that dimer coverings want to cover. And it turns out that even though the tilings can be completely random, there emerge some interesting curves, which are called limit shapes, actually surfaces and curves, which are unexpected. Let me skip this. So, and there is a kind of treasure trove of mathematical results in this field, which is called, I guess, integral probability. So I asked Borodin, what does he work on? And he said, it's integral probability. And I then asked him, what is integral probability? And he said, that's what I work on. So there's a bit of a, so I don't really know what that means, but basically it's very interesting, whatever that is. And so there are examples of papers which are not an easy read, but once you understand it, you say, oh, that's really cool. So in my naive view of the big picture that emerges from these papers is that these limit shapes are sort of quote unquote holographic projection of some surface associated with the so-called Castellan matrix. And so there's some big structure that exists. And the idea, so the reason I'm giving this talk is that when we were talking to Borodin, so I mentioned that dimer models appear naturally as ground states of quantum spin models. So it might be interesting to look at their results in the context of this emergent structure. So and essentially, that's what I've been trying to do. And this is what I want to talk about today. But I need, before connecting the two fields, I need to tell you basically what I'm talking about these two fields. So now before I was talking about dimer coverings, and we were studying them because why not? But also they emerge as ground states of, well, quantum dimer models, and I'll tell later also of quantum spin models. And the first Hamiltonian, one of the first kind of examples of that was written is due to Rockshire and Kivelson, where you have two terms. One term flips the flippable plaquettes, let's say on a square lattice. I will be mostly using square lattice, but it's actually much of the stuff I'm talking about is generalizable to arbitrary lattices and graphs. And this term assigns potential energy to dimers. And so there is a phase diagram to this model, which is interesting, but of particular interest is the RK point where V is equal to J, in which case the model, we know exact ground state of the model because we know that the energies are positive by just squaring this thing. And we also know that dimer coverings, just the perfect matching of whatever lattice we're dealing with, is indeed the ground state. So in this case, the dimer covering appears as the ground state of a quantum Hamiltonian. So, but even though we know the ground state, it doesn't automatically tell us that what the underlying phase actually is. To figure this out, we need to take this ground state, and depending on the parent model, we may want to calculate other types of correlators. Let's say dimer-dimer correlators. I'll talk later about Wisen-Wisen correlators, monomer correlators. And depending on what we see with these correlators, we have different types of states. So say on a square lattice, you will observe power law decay of the dimer correlations, which will correspond to a critical point. In certain lattices, you may see the exponential decay of everything, which is kind of interesting because it corresponds to spin liquid. And also, of course, we can have just ordered state. So I'll mention in passing that the RK Hamiltonian can be generalized to generate just about any dimer cover I like. So let's say if I just choose any weights I like on a lattice and I ask, can I create a local Hamiltonian to which it's a ground state, the answer is yes. So and this can be done. Well, I don't expect you to be able to go through this algebra in real time, but it's not super complicated. So essentially, there is a way to construct a variation of the RK Hamiltonian such that any cover you like becomes its ground state. So, but the upshot of this is that any Gibbs measure that mathematicians study, basically the assignment of weights, of a dimer model is realizable as being emergent from quantum lattice models. So this is, so far has been just dimers, but one can also build a RK model and the like from spin models, which follow actually the earliest construction by Lenz, Fisher, and Gervin. And of course, Leon and Matthew are part of this collaboration. Also, we had somewhat related paper with Ashwin on this, but there are many papers. So I'll present a more simple construction of how it works. So what I'm doing now, I'm just saying, oh, actually, the physics that I'm trying to embed sort of can appear within quantum magnetism. So, and how it works is let's say we have a square lattice and we cover it with dimers. So this is one dimer per vertex. So let's connect the dimers, the centers of the nearest neighbor edges by lines. So you create sort of a line graph. And what we do, we simply assign, if there is no dimer, you will say that it's a spin up. And if a dimer is present, you say it's spin down, in which case it becomes a spin realization. And spins leave on the edges of the original lattice on this line graph. So you get this. And then now this is just a mapping between dimers and up and down. But you can also actually create a Hamiltonian if you implement a gauge constraint, which ensures that you have only one dimer per vertex. And this corresponds to this simple constraint. And once you're done with that, so you can construct Hamiltonians. For example, and by the way, it can be enforced just energetically by setting U to infinity and just requiring that there are 4 spins going around the shaded plaquettes. So one of them is down and 3 of them are up. That corresponds to having a dimer. But then we can also create all kinds of Hamiltonians, including the ones that will realize the ring exchange and the potential energy. So the bottom line here is that even though I was talking about quantum dimer model, I can also talk about quantum spin models, realizing just about any dimer covering as its ground state. So now, so this was kind of the physics part of it. But now I want to mention something which actually still shocks me. So the original paper was written back in '98 by Peter Shor, James Propp, and William Chakusha. I don't know what this affiliation means. Yeah, so but it is really a magical paper in my opinion. So, and what it does is it studies basically domino tilings that already introduced on a square lattice, but bounded by different types of domains. Now, again, if you just do the simple thing, you generate a bunch of random domino tilings. There are different colors because it's a bipartite lattice. You can color them differently depending on whether it's AB or BA. So you can do that, and you can calculate the dimer-dimer correlation function. It will decay algebraically. Now, if you take a different shape, let's say this shape, which is called Aztec diamond, and you start tiling it, so you will kind of have to enforce this configuration most of the time. Otherwise, it's not going to work. And you may say, like, why do we care about it? Well, if you grow it, so these boundary effects should disappear. But they do not. So if you actually generate now, you don't even know that it's Aztec diamond. It might have been just a rotated square. So if you now generate a huge thermodynamic limit, basically shape, so you will see very clearly that there are several regions at the macroscopic regions, at the edges, and in the center, where actually the behavior of the dimer-dimer correlations are completely different. So in the corners, you have an ordered state. And in the center, you have the power law state, which is kind of a liquid state. And the curve that separates the two is called, Shor and company called it Arctic Circle. It's almost a perfect circle. So that's very interesting. So now if you, and you can do now other experiments, numerical experiments by assigning different types of weights, let's say periodic weights. So this, for instance, double periodic weights. In this case, you will see also corner phases, the power law, and the exponentially decaying correlator in the middle. And so these curves are called octet curves. So mathematicians figured out how to even calculate these curves. So there is some magic going on where the results of dimer covering depends on the boundary conditions. So a way to understand it, and I kind of borrowed it from Alexei's webpage. You can play around with it. Just go to his webpage and see he has very nice animations. So the way to understand it is to assign, to kind of lift those dimers or dominoes to 3D, to assign height function to them. And one can do so per this assignment. So it takes maybe 3 minutes to digest it. But the idea is kind of simple so that you can, instead of thinking about them as planar, you go up and down. And if you extrapolate this construction to larger systems, you actually can prove that you will get smooth curves out of it, smooth surfaces in 3 dimensions. And this is an example of the Aztec diamond now plotted as a 2-dimensional surface embedded in 3-dimensional space. And what's happening here, and one of the reasons kind of quote unquote thermodynamic limit is violated, is because in this height function, you almost like enforcing, it's like hanging a tablecloth at different heights. So you enforce the corners, and there's nothing the system can do about that. But it doesn't really explain why you have such a variety of phases in the middle. But it's a nice intuition. So this height function is very important. So what we did, and this is one of the first papers we wrote with my student Jit Shah, who just moved to Amazon Quantum, Laura Shu, who is actually a PhD from Princeton in pure math and UQM postdoc. And this guy who joined, who is scary, he became a student at Cornell at 12. And he tried to do quantum gravity, it didn't work out, so he ended up with me. And he is now old, like 23 or something. So anyway, so this is the attempt to essentially marry the two fields to say that, okay, well, so there is this interesting stuff going on with dimers on these Aztec diamonds and other shapes. And we know that dimer models do appear as kind of byproduct of quantum spin models. Why don't we just marry the two? And that's basically what we did here. And I won't bore you with all the details. I will just say that it's possible to create spin Hamiltonians, which don't look necessarily very pretty, but they're local and well-defined, whose exact ground state is known, and it corresponds to, let's say, in this case, uniform dimer covering of the Aztec diamond. So we do that, and we observe, therefore, that you have something very interesting. So you have a spin model, which in thermodynamic limit, if you take a simple square, is just a critical liquid, and there are power law correlations. But if you do Aztec diamond, you can't even tell if you look from a large distance. You can't even say that there actually any difference between the two. So there is this kind of phase separation with liquid in the middle and ordered phases, or the spin phases in this case, in the corners. But we didn't really like very much the fact that it's a liquid. The reason being is that this liquid is really a critical point. It's unstable. So let's say in the original Rorschach-Kevelson model, if you remember, there was a ring exchange terms and potential energy terms, and the liquid emerged and the exact solution emerged only when J was equal to V. If you deviate left or right, so it's supposed to become an ordered state. And actually, I haven't seen it yet in simulations, but it appears likely that this liquid is unstable. But it's amazingly stable if you start modifying the weight. So here it's just uniform perfect matching, but if you start multiplying it by some random, basically random weights, it's still kind of, this picture still remains. So it's kind of robust against that. But I'm not sure if it's robust about quantum fluctuations. And we also checked if it's robust, whether it's robust against killing the height function. And so far, I know we discussed it with Zohar a little bit. So, and unfortunately, it gets melted. But anyways, let me just go to a more interesting case. So what we wanted to get an interesting phase where you have exponential decay of correlations. So I personally wanted to get quantum spin liquid, Z2 spin liquid, being embedded in these Aztec diamonds, et cetera, et cetera. And for that, you need more complicated lattices, which is no shortage of. And mathematicians have figured out how to construct dimer models where you get areas with exponential correlators. I likely will run out of time, so I'll say I actually couldn't find the spin liquid, but we could find something, I think, which is much more stable and interesting. And for that, we need to go to a model that gives me just basically to steal something from mathematicians and go to a model which shows exponential correlations, and it happens to be this weird model which we call square octagon lattice. So you can actually, it's kind of a nice numerical exercise. You can do it all day to try different types of lattices, put them on different types of shapes, and you will see kind of all kinds of phase separation. So in the particular case of this lattice, if you do it on a simple square lattice, you get exponential correlations of dimers, exponential decay of correlations. If you put it on this diamond, which is this Aztec diamond or fortress, you will see now 3 regions. So in the corners, you will have an ordered state, which you kind of can see, basically. It's something like this. In the middle, you will see a liquid region, which was just like before. It's just like a square lattice dimer covering with uniform weights. But in the very middle, you will see a region where dimer correlation functions decay exponentially, and we actually could even calculate the correlation length. So it's very interesting, because the reason I like it more is because exponential correlations means that presumably this phase is more stable than power laws, the critical phase. So this thing may not be just an artifact of some fine-tuning and integrability, but may be stable to a class of perturbations. So that's kind of why we went into trouble and studied this shape. So mathematicians normally study only dimer-dimer correlations because their dimer covering is equation number 1. So it's not an emergent thing. It's just they start with a certain Gibbs measure and just go from there. So, but if our dimers appear as emergent phenomena from other models, let's say quantum spin models, we may want to care about other things except dimer-dimer correlations. So let's say if we're curious about whether or not our model is a spin liquid, we need to know that whether there are magnetic and electric excitations, and this translates into calculating not only dimer-dimer correlations, but also so-called Wison-Wison correlations, which I think Sentil and Fisher introduced some time ago in the context of cuprates, but obviously it's much more general than cuprates. So the dimer-dimer correlations mean that you freeze two dimers, don't touch them, and you basically count the number of all possible dimer coverings with this guy's fixed divided by the partition function, which is just the total number of dimer coverings. And you get a result, which is a function of the distance between the dimers, which may be a power law, exponential, or constant. So a Wison-Wison correlator, which corresponds to kind of magnetic charges in the gauge theory, in Z2 gauge theory, corresponds to, you take two plaquettes, you fix them, you draw a line, which actually doesn't matter through how you draw it, it should be independent. You draw a line and you count the number of dimers it crosses. If it's even, you assign to it a +1. If it's odd, you assign to it a -1, and you sum over all possible configurations. That's what it means to calculate Wison-Wison correlator. So, and what we want, kind of, I mean, what I wanted, it was to see a model where dimer-dimer would decay exponentially, which already did. So I was hoping maybe it's a spin liquid. But we also needed to make sure that this guy, not make sure, to check whether it decays exponentially. And unfortunately, actually, it's not in this particular case. And if it's not, it means that there is some hidden order or something funny going on. But it's not a spin liquid. So this is a calculation of the dimer-dimer correlator. And we have been able actually to calculate analytically the Wison-Wison correlator. It happens to be square root of 60/10. It's a constant. It doesn't decay at all. So, and it turns out that in this case, essentially what we're dealing with, so if we go back to the spin model, so essentially you have normal ordered spin phases, nothing fancy in the corners. You have a critical liquid in the middle region. And here you have sort of a slightly perturbed product state, which is, yeah, it does have exponential correlators, but it's not super interesting from the entanglement perspective. But it's still interesting in the sense that if I now turn this thing around and just study it on a perfect square with no add stack and no funny corrections to the boundary, you will see nothing but this phase. So the corners will melt, the liquids will disappear, and you will see just one phase. So I will, yeah, so this is sort of hopefully was just to motivate, your interest potentially in these types of phenomena, which are interesting and just curious, where basically I would say thermodynamic limit is questionable in some sense. But I wanted also to mention a little bit the technical side, which is super interesting. So I won't be able to give it justice because mathematics there is extremely deep, and I don't understand it. But I just want to give you a flavor of what we actually do to calculate stuff. So, so the calculations are based on generalized Castellan metrics. So dimer models originally appeared in the context of chemistry back in the 30s and kind of developed in the context of roughening transitions in the 50s by Castellan and Michael Fisher, Matthew Fisher's father, and others. And so it's an old subject. So, and the main object that you have, and let's just think about, let's say, square lattice, is adjacency matrix, which is very simple. If two vertices, black and white vertices, are connected by an edge, you assign 1 to it. And if they're not, they're assigned 0. And that's it. So in Castellan, Castellan figured out that, for instance, in order to calculate the number of possible dimer coverings, you just need to enrich this adjacency matrix with sign assignments. So you kind of put the orientation on your lattice. And if an edge goes from black to white, you assign to it a +1. And it should be the other way around. And white to black, -1. Oh, yeah, sorry, no, it's OK. If it has positive orientation, it's +1. It has negative orientation, it's -1. And yeah, so this matrix turns out to be extremely powerful. For example, the determinant of this matrix calculates the number of dimer coverings, 5 minutes, okay. And for example, if you're interested in dimer-dimer correlations, what you actually do, you create this Castellan matrix. You calculate this inverse, which just can be done by a Fourier transform, like band structure. And dimer-dimer correlator is simply, let's say, if you have 2 dimers at 1 and 2, so there is this object. And in principle, you can calculate anything you want. And so I guess a little progress sort of on the computational side here. So we figured out how to calculate basically by pencil and paper Weizen-Weizen correlator. You just have to modify a little bit this Castellan matrix, and you can get results like square root of 60/10 versus running Monte Carlo. So if we look at papers, let's say by Leon, Matthew, and Steve Gervin, so one of the first papers, so we need to run Monte Carlo to check Weizen-Weizen correlator. But I think in many cases, you can just calculate it. So anyway, so this is kind of nitty-gritty a little bit of the classical StatMech calculations, which sort of have been known forever. I want to mention another thing which I really don't understand. Does make sense to me. It was based on a discussion with Amol Agarwal, who was at Columbia. I think he just moved to Stanford. He's a mathematician. So we oftentimes are interested, well, if we're thinking about this dimer models in context of Z2 gauge theory, so well, we calculate Weisens because it's Z2 gauge theory, but also we want to calculate Wilson loops. And Wilson loops are supposed to be independent of the shape of the loop. But the Z-stack phenomena tell us that actually that's not true. So for instance, you take a certain, well, this model that I had just shown you, just in an infinite space, so no funny business with boundary conditions. But you kind of restore this Aztec boundaries by considering genetic loops versus special loops that give you this phase separation. And here are the calculations based on exact integer arithmetic with arbitrary precision calculations. So you see very, very small numbers. So if you take a generic loop and calculate the Wilson loop, how it scales, its fit is perimeter law, but this guy is area law. So, and I don't understand it, why it's happening. So I think maybe time direction is really important, and sometimes Wilson loops can be misleading if you just calculate them in space. Now, the last thing I want to mention, so we started a little late, so I still have 1 or 2 minutes. So I wanted to just give you a flavor of the most beautiful stuff, which I really don't understand, but I think that's really cool. So what kind of attracted me to this field? So mathematicians understand the appearance of this boundary phenomena from a very general perspective. So, and this is primarily work by Okunkov and Borodin and collaborators. So, and the way it works is that let's say you have, let's say bipartite graph, let's say square lattice for simplicity with periodic weights. Let's just establish that. It's more general than that, but that's kind of not the point. And well, it defines fundamental domain, basically elementary cell, just like in solid state physics, because of periodic weights. Let's say of width k and length L in 2 dimensions. And what they do, they define a certain, they call it magnetic Castellan matrix. It doesn't matter why it's magnetic, although it has a relation to gauge theory, where they assign additional additional weights, to one part of the, let's say this right part of the fundamental domain, and weights z-1 to the down part of the fundamental domain. And as a result of this exercise, they now get a new matrix and calculate so-called characteristic polynomial, which is simply the determinant of this matrix. Again, this matrix is not too complicated. It's just if edges are connected, you assign 1 or -1, and enrich it a little bit with these complex numbers. And once you get this, and I'm just reciting the results without explaining why, primarily because I don't actually understand why, but the results are interesting. So you take this object and you basically study its algebraic curve, which is basically setting determinant of it to 0. And it gives you some sort of a surface which is provably has genus k-1, L-1. So for example, if periodicity is 4 and 3, it will be 3 times 2, and so you will have genus 6 surface. And the main result, basically, and this is where I want to leave it, is that the mathematicians understood that this surface is really where everything lives, basically. So there is some smart way that Borodin established which can connect the shapes of the certain Aztec diamonds, et cetera, to the prescription on how to construct this Castellan matrix. So they can construct this algebraic curve and then project it back in 2 dimensions. So they projected by, so obviously I can't plot anything in 4 dimensions, but you can sort of project it into 2 dimensions under this. So you just take determinant of this matrix with 2 complex numbers, set it to 0, and then plot log z and log w, and gives you 2 by 2 curves. And these are called amoebas for some reason. Well, I guess because they look like that. And it's interesting that it goes both ways. So you can reconstruct this from this, etc. And there is a one-to-one correspondence between the shapes that you get here and the shapes that you get in your domino tilings. So for example, these holes correspond to exponential decay of correlations, which either are product states or maybe even spin liquids. So the middle one corresponds to a critical state in my language, and the outer ones corresponds to frozen ordered states. That's very interesting. So with this, I'm basically done. I had another plot just saying that there is some interesting physics with the fluctuations. It follows KPZ physics. So but all in all, we're dealing with some very interesting structures where you have line shapes and other things. And it's actually maybe relevant to some experiments, but I don't have time to discuss it. So I will just say that I will just finish with acknowledgements. So primarily discussions with my math collaborators, Amol, Alexei, and more recently, Ivan Korvin. So I didn't really get to talk about it, but I'm also collaborating on this with Sarah Miller from Applied Research Lab for Intelligence Security over in Maryland, who also kindly provides funding through DoD. And these are the people who've been doing all the work. Thank you very much.
Ends at 1:30. So
No, that's not right, actually.
Oh, that's
I was wrong about that. So we have time for a couple questions.
In 2D, simplemente this timer discuss the matrix and timer forwards have something to do with 2D experiments and collective. In relation to 2D Kaplan variables, collective, I think.
So what's the question?
So does the quantum system have a society?
Yeah, so there is actually Sasha Banov is working on this type of mapping. There are many types of mappings. Depends on kind of almost your taste, what you like. So it does have relations to fermions. I mean, I guess you can. Yeah, it depends on exactly what you're trying to actually figure out. The answer is yes, but I don't know what you're asking. Like, what has relations to what? So there are certain things. Actually, Sasha Abanov, I don't fully understand his papers, but he can rederive all these Arctic circles, et cetera, through just fermionic theories with some additional constraints and write some hydrodynamics there. So I think maybe Zohar, you know probably much more about it than I do. So, but the short answer is yes, you can reformulate it in fermionic language, and it's sort of interesting. It maps on generalized hydrodynamics, if I understand correctly.
Yeah. This use of the Castellan matrix to count dimer coverings only works for planar graphs.
Correct.
I was wondering whether this phase separation phenomenon mentioned happens also more generally.
Yeah, actually, there's one paper on that, exactly one paper. I mean, actually, it's sort of irrelevant. So if maybe let me go back if I can draw. Actually didn't go over this. So suppose you just want to calculate the number. What? Yeah, so just want to answer your question. So suppose you want to calculate the partition function, that is the number of dimer configurations, possible dimer configurations. Actually, if you have a general non-planar graph, it's a Hafnian of the weight matrix, which is actually computationally, in the worst case, actually sharp P, very difficult. If you have a bipartite graph, I think it's permanent of the weight matrix. If you have a planar graph, it's a Pfaffian. And if it's bipartite planar, it's the determinant of the Castellan matrix. So, well, there is, yeah, but first of all, I mean, there are two questions. Like, first, is there a Castellan in high dimensions? The answer is no, basically. And the second question, are there limit shapes in high dimensions? The answer is absolutely yes. And people have looked at it, and we actually looked into it too. So you get spheres and all kinds of stuff, but there's like mathematics is totally missing there. I have no, I mean, you can see that, but I don't know how to quantify anything.
Yeah, I was just wondering, this area, perimeter law for Wilson loop, that's not just the fact that the Wilson loop, there are different phases within the Aztec
No.
diamond.
No,
It's not.
Oh, it's the same phase.
So
It's actually as a puzzle. Oh man, so
you have crystalline regions and the gapless regions.
no, actually no. So you take, so that's why I'm surprised. I mean, actually it was a question. It wasn't like, oh, I know what's going on. It's an observation. And I would be happy to know what's going on. So you have now a lattice which is uniform, just infinite lattice in 2 dimensions. And what I'm saying, which was kind of, again, based on intuition by mathematicians, is that I can micromanage my loops in such a way that they cut out. So when I say calculate Wilson loop, what does it actually mean? You freeze some dimers along the loop, you permute everything else, but by doing so, you essentially cut out the exterior and interior, right? So if you have a loop, they don't talk to each other. So this stuff with the boundary conditions, etc., reappears again. So, and that's the origin of the different scaling. So I think the message here is that we just can't actually use Wilson loops to characterize our phases just in space. I think that's, so I think there are papers actually including by David Hughes and others, which argue that, well, maybe you don't really need to go into time. Maybe we can just do it in space. I think it's just not true generally. And it's just an example of that. So I don't think it has any deep meaning apart from just like, you know, we calculate Wilson loop for a reason because there is time. And here we're just dealing with space. So that's my conjecture, but I actually don't know. It's kind of weird. But
It's really good. Let's thank Victor.